Okay, so let's go ahead and get started here. So welcome to our ML deployment in TensorFlow. So sequential model is appropriate for a plain stack of layers where each layer has exactly one input tensor and one output tensor, meaning that it's inputting one piece of data and predicting one piece of data. So the shape is key here. That's kind of one of the things we talked about yesterday when we were naming the shape argument. We need to decide what it's going to be. So when we're working with this, each model here, or each layer of my model has one thing going in and its output is one thing as well. Here, a sequential model is not appropriate when if we have multiple inputs or multiple outputs. So if we're trying to take in, multi-dimensional column data or predict more than one thing. If any one of those layers has that, so again, it's all or nothing. You either have all single input data that's predicting a single thing, or you can't do it. You would have to use a different type of modeling, sharing layers, or a non-linear idea here. So something that we're looking at that's not directly predictive, whether it's classification or regression. So are the above and below blocks of code here these model definitions? So we talked yesterday about the different ways to build models. So are these two going to be the same, or are they going to be different? These are the same model. This is just two different ways of creating the same thing. So this would be one way of doing it, where we've seen yesterday we defined, good. So we defined it layer by layer. So you've seen me define it yesterday as a layer 0. And then we also talked about how here you can just do it all within a list. So we'll kind of see both ways today. And they do the same thing. It's not going to make much of a difference. Typically when I'm in like a development or testing stage of a model, I like doing it like this because then I just kind of find it easier to replace one thing. And I can kind of see the clear, where is it going? Which layer is it? Whereas here, you can kind of also read it vertically, and it's actually pretty nice to change in place here as well. So kind of you can compare a little easier. If you want to compare model performance, it's here. This is more of a nice like kind of sequential edit on the fly type thing and reads a little cleaner. So our goals for this session, we're going to be using Keras and TensorFlow to develop a model. We're going to discuss sequential models. And of course, we're going to build a sequential model. If we don't build it, not much to discuss. So I'm going to go ahead and open up that new Jupyter notebook file. So just as a review, the data we're going to be working with today is a lot of handwritten digits data. So this data set is known as the Modified National Institute of Standards and Technology Database. That's what MNIST stands for. What this is going to be is basically it's a combination of employees from the US Census Bureau, as well as a bunch of high school kids sampled at random here that created our data sets. Now, when this data set was first trying to be implemented, a lot of different researchers originally used the Census Bureau's data. So all the adults working there is the training data, and then attempted to use it to classify the high school side to it. So they took the professional level adult of here's your data, here's how you write numbers, and they used it to train it on the high school students, and they got very poor results. So it was at this time they realized that their sample there probably wasn't too accurate, because you're going to compare the way a lot of fully employed professional adults are writing something versus the way a lot of high school kids may be writing their numbers. So they then kind of used a combination of both of those two samples together to create the new version of it. That's where we get the modified from. So the original data set was just the NIST, and that's where they kind of realized pretty tough to compare those two. So when we're working with human input such as this is kind of where we want to have a nice wide variety in our sample. So kind of seeing those different things. So our goal today will be to input the data in a preset way. What's cool is that this has been one of those things where it's like nicely built, where we could import it pretty quickly and have it like the setup is pretty smooth, and it's more so just kind of understanding the process that we're going through it. So we'll talk a lot today. Will be like I'll put code in and then we'll talk through it just for the sake of make sure I type everything right the first time, and then we'll kind of comment out our code that way. All right. First, I'm going to go ahead and share our imports. So if you open up that shared file, they are in there. Oh, is it not like it? Oh, that's right. We didn't install Keras yet. So to get Keras in here, so this Keras, you can go ahead and install it. So yesterday, if you remember your Anaconda command prompt, okay, so I'm gonna go ahead and rerun mine. There we go. So if you have to install again, if you're running Windows, Anaconda command prompt. So if you run this and get the error on Keras, it may not be installed on your end. So to install it, if you have to, Anaconda command prompt, and then you're going to say pip install Keras. If you're running on Mac or Linux, so again, you would just use the terminal for that. All right. So talking through things here, we should be pretty comfortable with NumPy, PLT. So these are our two kind of go-tos. Random is just use the generated, we need randomized effect of like shuffling up data. This is something we'll use here. So you have multi-class, two categorical. So we'll see that how to shift those images into the idea of categories we could place it into. Here's some of our optimizers. We'll do a little bit more research later on and some of the different optimizer options we have. Dense for our layers. Here's the data set itself. So again, this is a nice little call to get that data. And then again, sequential for the type of modeling we're going to be doing. All right, so the first thing we're going to do here is we're going to get our images. So I'm going to kind of type out exactly how we want to do that. So this is going to be our importing the images. So what this is doing is it's pulling in our data into the predefined training and testing data sets. So something that's actually pretty common with large scale publicly available data like this is they are very well much used in like, academic communities or people trying to show how good of a model they can build and seeing how low of an error rate they can get on this. So building different types of networking, neural networks, whatever it is, learning models, and seeing how well they can classify these images. I'm trying to think, I think I had it written over here. I think the lowest one is around like 0.5%, maybe a little lower. I think that was the last time I looked. It may be a little lower than that even in terms of their error rate there. So we'll see how good we can get today when we're building our first model here together. All right, so let's go ahead and look at the shapes of these things here. So let's see train shape. We want to make sure our test is the same. And if we want to look at like the first thing there, if we just look at this 0th row. So here are our shapes. So kind of the difference here, we have 60,000 in the training, 10,000 in the testing. So you can see, again, we have a lot more training than testing. So again, these are kind of evenly dispersed between where the data came from. And then we see our training output here. So what we're trying to match it to. So it's those 60,000 different things we need. All right, let's move on down a bit. And let's start building our first thing here to kind of, what we're going to do is visualize some of the data that's coming in here. So this one's going to take me a minute to type out. It's quite a lot of lines, but then we'll talk through it together. So here we have some three-dimensional data. So if I look at what this just looks like with just X train here, So it's an array of arrays. So that's where we kind of get that three-dimensional piece to it. So again, we had that three-dimensional output here where we have X, Y, and Z. So what that is reading it is this is if I just call Xtrain and just print it. So it's an array of different arrays. So awesome question there. I know this one's a bit lengthy. It makes a really cool visualization that we'll be talking through in a minute. And all right, let me just do a check here, make sure I have this good so far. Good there. And I want TI again. All right, make sure we run this the way I want it to. Oh, what are they not liking? They're saying, that explains it. I had an E here, and then I didn't have any E's down here. So E, E. Okay, so this is what we were getting. Now let me talk through how we actually do this. So first, all right, so first thing we did here was just create a blank list for our number of samples. Here we're picking out our thing. So what this is defining is how many columns we have. And then the number of classes, so the numbers 0 through 9, so the digits 0 through 9 were our number of classes. Here we created our images, so we created the grid that we wanted to plot to. And then let's go ahead, I'm going to comment this out as well here. So the first line here, when we do this, the tight layout Think of it as removing extra white space. It just kind of is a standard way of making it look a little cleaner and avoiding any kind of like weird formatting. And then this part is actually how we're populating this grid. So how we're putting these images in there. And again, because of the way we're doing this here, we'll talk about this in a second, it should look a little, could I should say, look a little different on each of our sides. So if I ran this again, you can see that each time it's pulling randomized selections there for our visual. So for this one here, this is getting our size. So this is considered an outer loop because it's the first one here. This one here is going to be our inner loop. So it's looking at a number of classes or rows. Here it's saying which X's we are picking. And then this part here is where we're saying to actually show the image. So this show here tells us to show the image as opposed to showing the array. So when we looked up here, we have an array of arrays. Hence how we get that three-dimensional shape here. So when we said what the shape of X-train was, when we did this, the third dimension here is being the array within a array. So what that is doing is telling it to actually show the image and then which ones I'm choosing. This line here, that's where we imported that random for. So it's saying just pick a random integer between 0 and then the length of that array or those selected X's there. And it's saying here to tell us, okay, we want one less than however far it is. So it's picking a random one from somewhere in there. The color map here, let me go see if I can find a cool thing for you guys on that. Where are we at here? So if you just Google CMaps, so CMap options, you can find some cool stuff on there if you're looking for those later on. However, with this, it's kind of easiest if we just use that grayscale. And then turning the axis off here, it gets rid of like grid lines, so it just looks a little bit nicer. And then lastly, it's just saying what to set the title equal to here. So this 0, this 1, so it's just a string that we're calling on to get those. So this is our grouping of 0s, 1s, and then all the way through. All right, so let's go ahead and look a little bit here at the different types of samples we have. So kind of seeing what they look like, how many we have of each. So what I'm gonna do now is build a visualization for this. So let's go ahead and see what we have here. So we have our number of samples that define how many were in each. So let's go ahead and first thing we'll do is we'll print out that num of our samples. And then let's go ahead and build in a figure here. So again, that fig size command there just says how big the plot we want it to be. We can adjust that each time with that command. And for this, since we're doing into categories, let's go ahead and just do a quick bar chart here. All right. Forgot one thing, plt.show, just so we make it look a little cleaner. So what this is doing is the first thing here is it's giving me the actual value count for each. So you could do it this way. Sometimes though, having a visualization does help. So this is an order here, 0 through 9. And same thing we can kind of see here, what that's looking like visually. So this is the number of images, frequency here, and then this is the class. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, they're just numeric matching this up here. So when we're looking at this, we can kind of see here that, hey, look, okay, this is looking pretty similar. We can kind of see the different outcomes of each and how many that's roughly equal. So it's not like we're missing a ton of 4s or, 9s, like nothing sticking out as being like drastically underrepresented here. All right, so next thing we want to do here is let's just take a quick look at our Y data. So if I look at our Y training data here, what's a little different about this is the shape of the array here. So what we can kind of see being in there, it's not as, I guess you could say, it's literally just a list of outputs. So it's just a list of outputs as opposed to this 3-dimensional array we're working with here. So what we're going to do to make this more usable is we're going to make this an array of like in the categorical sense. So we're going to say to categorical. So that was one of our initial imports there. And here I'm just going to say Y train. And then we want those 10 different outcomes. And then I'm going to do the same thing here with my testing data. So this is kind of just reshaping that data in a categorical sense so that we can work with it. So it makes our data usable for classification. All right, and the next part here is a little specific to this data set. It deals with image intensity. So the images have what's called intensity, and that's one we don't have a whole lot of time to go through today. But if you're going to go into image classification, are you going to work with that? It's something you want to account for in this. For the sake of our training today, what we're doing is just doing some division here to kind of get the intensity scaled the way we need it to. So this is kind of the end of the prep work here on what we'll need to do with that. So if you're looking for a read up on the idea of image intensity and why we do some transformations on it, that would be some extended work that Geeks for Geeks article I just posted there, where it kind of goes through more of understanding in terms of what image intensity is. Okay, this is another one here where we have to do some transformations here to work with this data. So what we're going to do is we're going to be changing the shape. So when we're getting this out here, we're going to get this, I guess you could say, just transformed to the way we need it to be. So if we think about the shape that we're going to need from this, so we have these 28 by 28 arrays. So if I want to get it into a one-dimensional, if I do 28 times 28, I get 784. So to figure out how big it's going to be here. So what we're doing is we're taking these images that are classified as these, kind of array shapes, and we're putting them into this. So those images are classified basically by this ones and zeros, just kind of classifying out the drawing, but we need to be a one-dimensional array so that we can use the sequential model. So the first thing we're gonna do here is get our number of pixels. So we're just gonna use that as 784. because again, that idea of 28 times 28, so 1 times 784. And then we're going to say xtrain is equal to xtrain dot reshape. So this is another thing here when it comes to reshaping arrays. That is a common practice whenever you're in kind of in like specified areas of machine learning. So getting the arrays to the shape that you need. So that's another thing if you want to do some further research to get good with that. And it's one of those things, honestly, from experience, I would say you learn it from trial and error. And learn as you go, research as needed. Also, again, that copy paste feature is fantastic when you're doing something to training and testing data. So it reshaped it here. So if we take a look at our training data now, we can see here it's just one incredibly large array filled with lists. So one thing I want to do here is actually go back and kind of give us a better idea of these images as well. So what I'm going to do is I'm going to share over a different screen here where I had some demo code. The only reason why is because I don't feel like I was having to redo everything. And you can only see these images at certain points in the code where it'll run smoothly. So I'm just going to go ahead and show something over here, just another file I have handy. So it's kind of working with the same data. But again, if we wanted to look at these at an individual basis, here's kind of the way they're being printed out. So these arrays are coming out looking like this. And here's what it would look like is if you had like a matrix. So the way we're looking at this number 1 drawn here, this is what it looks like in terms of those array. So this was our original array here. So if we're counting across and down, that's where I'm getting that 28 times 28 from. So 28 pixels wide and then 28 pixels tall as well, or length width argument. So this is these numbers that we're pulling in here. And then the different intensities in here represent how dark the coloring would be. So from the handwriting, how we have this darker in here. So this deals with the image intensity. So I figured this was a good, nice visual here of. So here's how to pull those things. If you do want to go back and include this, and I'll show you where to put it in our code too here. But yes, this is kind of a good demo dash here on how to figure out the intensity. So you can go through there and you can kind of see the different ways you can see that mapping that intensity. Now you'd want to use a max argument or maybe do a couple here to kind of see how high those intensities are. But what that do is we're normalizing the intensity, so that's not being factored into our modeling. We're just looking at the existence of pixels in the 0, 1 constant. So that's where that divide by 255 is. So we're scaling these between 0 and 1. So if I wanted to put those in my actual code, and it's up to you if you want to rerun with me right now to get this to where you could see these as well. But it'd essentially be right here before we do any kind of transformations. If we go ahead and bring these in. So in like your third cell, and then for this next one here, we need the linear algebra package to actually get this to show us that level of precision. What's it not like in? Where did I say numpy? Oh, it should be NP. And then xtrain is capitalized. There we go. There we go. So if you want to include those in your file, the main thing is we want to show these before we did any form of adjustments or augmentation to this, just so it'd come out that way. So just some other options on how to get a better understanding of that intensity with the data. So these ideas of these numbers here representing that intensity. And if I zoom out a bit, it should actually make this look a little nicer too. There we go. So now it gives us that kind of same thing. So I just played with the zoom on my Chrome window to get it to display a little nicer. So again, darkness is a higher number. That's the intensity they're referring to. Whereas if I look like at this pixel here, I can see these are my lighter ones as well as here. So I can see that that intensity there is indicated as a lighter number. All right, so I'm just gonna kind of rerun my code here, just all my transformations. are now properly transformed. That's, again, advice whenever you're working with a file is, rerun things whenever you want to go back to the top and change something. Just because since I called on those, I had to rerun it so that my training would be in the shape I want it to get those visuals. Whereas here, we want it in the more usable format. So let me go ahead and let me just head to the notes. I'll just verbalize it. So if we think back to the slides I showed at the start, it was the idea of the input for a sequential model. So the reshaping here is specific to the sequential model. So I'll go ahead and type up some notes on this. So if we're thinking about the idea of one-dimensional data here, and I just kind of switch and I'll talk about in a second here. So with the sequential model, we have one-dimensional input to match a one-dimensional output. So what reshaping does is it allows us to take those kind of two-dimensional data frames or those arrays. So if I looked up here, where were we? So each one of these, which if I printed them, they look like this. So this is two-dimensional because it's got, if we look here, the easy way to tell if it's one or two is how many of these there are up front. Here we had two. And then we see when we look at this individually, it's the shape here. So it's got rows and columns in that array. So that's one of our kind of go-to data structures is a NumPy array. So in order to do the way a sequential model works, we need to be the one-to-one. So one dimensional input gets us a one-dimensional output. So here, when we look at what it looks like, so here that array is now lists. So instead of the array being a list of an array of arrays, we now have an array of. So we transformed, if I look here, this is our transform data. So it's still within an array. So the data is being held in there. However, since we don't have those double brackets like we've seen before, we could see it's not an array. It's just going to be a list of data. And we divide it by that 255 just to kind of normalize things a bit. So predictions work better with smaller and like kind of more normally distributed numbers. So by dividing by our largest intensity, we just kept everything between 0 and 1. And again, when you have to reshape, it's more of a, like I said, kind of a you learn as you need to learn type thing. So when you're working with different data sets, the reshaping basically comes from the way the models are set up. So today we're dealing with a sequential model that's kind of the introductory level in TensorFlow, like where you need to get to. In terms of your first stage of learning, there are models that are specific for multi-dimensional data, but the sequential model is pretty useful for a lot of stuff like image classification. It's pretty popular, and you can build and we'll learn more advanced skills as we move along with this. But sequential models are pretty popular anytime it comes into classification type things. So even though it may seem like a lot of work and that there might be more complex options, this is one of those, Occam's razor, the simplest explanation can often be the best. So the same thing with our modeling. All right, so let's go ahead now and we're gonna start building our model itself. So we're gonna use a definition here, so we're gonna say def, and we're gonna go ahead and create our model. So this is one of those imports we pulled earlier, the idea of sequential, so that came from way up here. So getting that model, and we'll spend a little bit of time here once we get through this code block of looking at the different modeling options. Go ahead and I'm going to type this up. Okay. So I'm going to have everyone type that out. It is in the shared file as well. And then we are going to talk through what that is actually doing in a moment here. So once you guys have that code down for our model here, the easiest thing we're going to do here is I'm going to suggest that you actually embed that link in here. So that's a link that I'm just going to go ahead and something you'll notice that is very, very useful is opposed to just bookmarking sites is actually putting them in your code files. So here's something that, whenever I've discussed with someone how to work with TensorFlow, they ask me, like, where are these numbers coming from? Like, are you just picking random ones? Like, is there a reason I want them? And the big question we have here is the idea of this. So what is the activation? So if you follow that link that I shared, it takes you to the Keras documentation. And as great as I hope I am at trying to explain things, the best thing you can do is to look through documentation, get used to reading it, because it's like having a really well-versed teacher with you all the time. So when we go ahead and look at this, let's go ahead and talk through the different pieces that we're getting. So here's our different activators. So if I go to usage, this should be just the first thing. Yep. Okay. So making sure these hyperlinks work the way I expected them to. So a couple different ways to do it. But again, the idea of activations is typically how I like to use this, with just with the keyword argument here, as opposed to embedding them like this. So this is another option. Typically, you see people do it this way because all these kind of keywords are pretty short. So if you want to read through here the available activations. So the two that we're working with here, we have ReLU or ReLU, depending on how you want to say it. So it kind of explains what it is here, a rectified linear algebra unit. So again, keeping things linear, which is always ideal. And it's a pretty good performing model here. So it typically does a little better than Sigmoid, but if you want to try it both ways, so those are the two more common ones here, ReLU and Sigmoid. So Sigmoid is down here. So if you're looking here, the idea here of this is like Sigmoid's kind of sensitive to the numeric value types. So reading up on when to use what, that's more of a personal research type thing. Kind of really getting good at choosing your activators. Another very common one is Softmax. So we see this one as well in our fourth level of our model. The real zero vector to categorical probabilities. So the idea here, since we're working with those 0 to 1s, the idea that what we're looking at is the probability of it picking that occurrence. So how high or low that thing is scaled. So since we're doing a 0 to 1 scaling with our intensity, that's kind of the nice part here about using that softmax. So it's specific to this with the image classification. So again, that's definitely a resource. I'm not going to take up your time in class reading through it, but I would definitely say to check that out as well. Okay, perfect. And here's the one for the dense part to it. So this is the link that kind of explains a little more about what the dense means. So the different options in there. So you can kind of see the different idea of how that density works. So I experimented with some different numbers here and then kind of found some good ones for our tutorial that'll work there. So you can kind of play with those as well for those dense arguments and learn a bit more about those. So let's go ahead and run that. So my code saves. And then the compiling here, let me get another good one for that. So I thought I had these opened up already, but I had to update my computer this morning, so we may have lost a bit of those. So model.compile, find this here. Okay, here's a good one for the different loss functions as well. So in this part here in our compile command, the different loss functions here, so what we use for what and why. So you can kind of see the different ones here. So probabilistic. So since we have the probabilistic, that's the 0 to 1 concept. So we have that softmax, and then we have the 0 to 1 ratings of the intensity that we scaled. So that's why we're using this here, categorical cross entropy. If you're working with a regression, you've seen us use mean squared error yesterday. And then hinge is kind of a specific type of classification. We won't touch on that as much. We're going to be more so on the more common ones here. So if I want to look at categorical cross entropy, here's the full specifics of it, of the different options you have within there. So again, I'm not necessarily suggesting we read it all right now, but definitely something commenting out in our code will be useful later on. And then our idea of metrics here, this one we should feel pretty comfortable with. When we do classification, we're concerned with accuracy. And then the idea of this is another way to create a model. So we touched on two originally. This is how we can create a model with a definition. So this is another way here. If we go back to, let me pull that up real quick. When we looked at this slide earlier, so here were two ways we can create a model. We can create it directly, or we can create it by naming layers and then assigning them by this method. But again, this is kind of the other way of doing it. So there's two ways we've seen those are the same. Here's another way of creating a model. So just kind of building it with the model.add option here. So getting our layers in that way. So let's go ahead and create our model here. So by doing it as a definition, it's actually pretty cool how we can create it. We can just say model is equal to create model. And then this way, if I want to go back, so let's say I wanted to try a different one, it's pretty easy to copy and paste this definition. And you could like create model 1, create model 2, just that numeric ordering here, or you could just edit it and then rerun the code here. So that created our model. And then if I want to go ahead and look at my model.summary. So what this does is kind of give us a little bit of input on our model here and how we can read the output with it. So this is the number of parameters going in, and then our output shape there. And again, our good idea here is that all of our params are trainable. So if you're missing something there, that's something to look back at. So all of them are going to be trainable. All right, let's go ahead here and take a look at getting our history. So you'll notice the history keyword here. You can make this anything you want, but just kind of vernacular. So when you're reading future code, typically we just use the word history to represent like the training phases of that model. So we have model.fit. We're going to use our training data. So X-train, Y-train. We'll go ahead and say our validation split. Let's use like 0.1. Then we'll decide our epoch. So let's start with something small just so we can run it locally. Oh, also, this is something too that was like never really well explained to me at first. So a lot of times when you see code, just to make it more readable, we don't put it all in one line. And I never was quite explained early on that like you can do that with Python. You can put these little code fragments on multiple lines. So my advice is if you're putting in multiple arguments or inputs, put the comma first and then press enter. it just looks nicer lined up than if I do this. I don't know why that's always bugged me. If you enjoy that, go nuts, but commas are important in coding. So I always like to put the comma and then just press enter. And again, the spacing will be totally fine if you use the enter key there. So then we'll say our batch size. Let's do chunks of 200. For verbose here, let's go ahead and set it equal to 1, just so we can kind of see what happens. So our epochs are low on this one, just for the sake of the example. So we'll set that verbose. Again, we talked about it's how much information shows. So we'll show 1, and then we could just use shuffle is equal to 1 for how the data is going in. So if I run that, you guys can kind of watch on my screen while I put this over in our shared code. So regardless of what machine you're on, if you keep the epochs low there and the rows at 1, I'm going to go ahead and actually take a chance and run that. And then we'll talk about what this output looks like. So while everyone's running that, let me see if I could find a good read on explaining these. So we kind of focused on the heavy hitting ideas this far of we want loss to be low and accuracy to be high. So that's kind of the general rule of thumb. If you're looking for how to determine how good a model is, low loss and high accuracy. However, depending on what field you're working in, your superiors may want a little bit more than that. So again, like that's kind of like a lot of times I work with students, I talked about the practical versus the presentable. So the practical is you want loss to be low. What is low? Well, the lower and closer to 0 it is, the better. Now, if you have gigantic numbers, maybe a loss could be at 50, and it doesn't seem that off the charts like we see in some modeling if we have a big numbers. However, once you normalize, you want to kind of get the idea of loss in representation to your numbers. So our numbers are all between 0 and 1. So this first loss here at 0.86, like that's pretty bad, right? Because if my max is 1, that's pretty darn high. But as we see here, with only 10 epochs, we are improving. So we went all the way from that 0.86 down to 0.16. Here, accuracy, same concept. So accuracy is between 0 and 1. So we started off with 70% accuracy. I would not make any prediction based on 70% accuracy. If you told me the chances that I win the lottery are that, like, that's still not that good in terms of being able to accurately classify something. However, once we start moving on, we can kind of see it go steadily increasing. We get up to that 0.95 by the end. And then again, that documentation I shared over helps read a bit more into how these are calculated. So let's get our model a bit better here. So what I'm going to do is, first thing, I'm going to make this model just kind of run again. So what I'm going to do is I'm going to set my verbose equal to 0, just so I don't have to look at all of this output. And then for our epochs, I'm going to go ahead and just put 1,000 in, or 10,000. Let's go 1,000. That should be sufficient. So that one with just 10, that's a great way of seeing with the verbose 1 and instead of 10 of how it looks. This is just kind of going to give you a better model here. So I'm going to go ahead and run this on my side. And this one may take a bit longer, as well as have everyone run it on their side if they're choosing to as well. All right, so what we're going to do right now, just for the sake of time, I don't want to eat up valuable minutes with letting a model train with 1,000 epochs. I should have probably went with like 100 on that one. So for the sake of today, let's go ahead here. And if yours is also still running like mine, what I want you to do is just go to kernel and just do restart. Then yeah, so that's just a good way of stopping those from running. Pros, cons, when you do the restart option there, you got to go run everything again. So I'm just going to go do that. I'm going to go ahead and just run all of my cells again. But I do prefer the restart over the interrupt just because it allows to make sure that like anything that I don't want is now gone. Oh, and I just ran that one again. Bad habits. So I'm gonna go ahead and change these epochs. Let's just stick with 10 for now, just so it gets a nice quick run. So I'm gonna go ahead and leave it at 10, just so we can work through the visuals and kind of get a look at it that way. That's what we're gonna talk about next year, is how to visualize how our model is learning over time. So let's go ahead and run that with 10, because then we won't have to wait for 5 hours that going through. So I'm gonna go ahead and pause here for about 2 minutes just to make sure everyone didn't make the same mistake I did and keep running with that 1,000 epochs. So we'll use 10. Again, if this was gonna be a really large project, again, the more epochs, the better. It just gives your model more time to train. However, hopefully this next visualization here will show you something as well as in terms of like the value of the epochs, what they're being added onto. All right. So what I want to talk about here is how to visualize this and kind of see what's going on with it. So what we're going to do is we're going to say plt.plot, and then we're going to say history.history. And the reason I can call it like this, so if I actually check out the type on history, it's an object, but if we kind of look at what it looks like here, this might be a little more explanatory. I'm gonna call it with a print. Yeah, it doesn't like doing that. I will tell you, to reference history, it's kind of like referencing a data frame in the way that we can call on things here. So what we want to look at is loss. And then I'm going to say plt.plot history.history. I want to see if I could find a good thing here, loss. Okay, this one's a little less formal of a resource, but it's Stack Exchange. So if you're looking to understand the difference between loss and val loss, this will kind of explain that a bit here. But first, let's go ahead and get our visual, and then we'll kind of talk through how to interpret them. All right, so let's go ahead and get that first, and then we'll kind of use that little post there to explain through the differences here. So what this is looking at is the loss function, and then measuring val loss. And for some reason, val, like my first mind always went to value. It's actually validation. So this might be something you want to kind of pin in there as well of the interpretation here. So this is someone up here just kind of looking at the difference. And this is, like I said, a great thing, Stack Exchange, Stack Overflow, of people who post things that have kind of a very quick understanding. And anytime I forget something, I use one of these sites, honestly, to like look up like, okay, like what's the difference between this again? And as great as I think my notes are, having nifty links here to sites that already exist is only adding to your resources. So this can kind of walk you through a little bit about that as well. So essentially, again, the idea here is that it deals with validation versus loss being more of like the accuracy. So how much of your data is not being useful in model building. So we can see both of these things low. So here we started with a high loss. The validation loss wasn't terrible at 0.25. It kind of goes down, fluctuates a bit, and then we keep moving on here. So we see the more epochs over time, we're going down, but we're not seeing a whole lot of difference in these values. You know, kind of once we hit like 8, like epochs, we're not seeing a ton. Let me go ahead and just try running this on my side here. I want to try if we can, how long it'll take for if I do like 50, just so we can see the graph being a bit different. So I'm just trying to run it with something a little higher where we can kind of see a more expanded version of this graph. But the code is going to be the same here to get the graph, sort of regardless of how many you run. This is also pros cons of having a verbose of 0. If I set it at 1, at least there we go. I'd at least know how close I was. So here we can see as we expand those epochs, we actually see a lot more fluctuation. So I could see my validation loss is actually increasing the further I go along here, whereas my loss overall is decreasing as those epochs. So finding the balance of how many epochs you want to use kind of deals with looking at these graphs of where they end up diverging at. However, now, if we want to go ahead and look at the accuracies, so I'm just going to go ahead and do a little copy paste here. So I'm going to do Control A, C, and then Control V here. So what we're going to do is go ahead and change this a bit. Now let's look at accuracy. And then my validation accuracy. So if I go ahead and run this, we can see that validation accuracy, again, kind of spiking up and down throughout. Whereas accuracy, generally speaking, will rise as we see in loss fall with more epochs. But again, we want to kind of get that like happy medium here of where, in this case, I wouldn't necessarily want to go all the way to 50 because I'm noticing this validation accuracy is dropping. So maybe right around like 20 looks pretty optimal here, where they're both pretty high. Right, so I'm at 0.950 on my accuracy. I get higher up here with more epochs, but then like I'm noticing this validation spiking downward. So this would probably be my optimal. So maybe around 20 to 22. And if I reference that up here, same concept. I'm seeing that spike downward here. So maybe my optimal amount here is about 22, where I'm getting a pretty low loss, pretty high accuracy, but those validations aren't spiked kind of out of control. So I'm gonna go ahead and back here and just retrain this with 22. And let's see how that looks. So this is kind of the purpose of the visualization piece here of kind of looking at how many epochs are ideal for yours. Again, if you run it at crazy high numbers, good. So we have a decrease here at right about 22. We see that spike downward and we see kind of stagnant loss, which is good. And then here, same concept. So we kind of found that ideal measure here where it flattens these out. So we're at kind of a plateau here and a plateau here. All right, so let's go ahead and see how this thing works. So let's build in some scoring. We go ahead and put this one, I forgot to update this. All right, there we go. All right, so let's go ahead and say score is equal to our model dot evaluate and we'll start with the verbose equals 0, just so we can kind of see. And then we'll print out to kind of see how we did. All right, so looking at this here, so our scoring versus our test accuracy. So I'm gonna go ahead and get you guys a resource for interpreting that. So there's another resource there of looking at the two of these things side by side. So we're looking at model evaluate model.predict. Here's something that can kind of walk you through that of evaluating, compiling, and then the predictions piece here. So that model.predict just turns the predictions, whereas evaluate gives us those two options. So if you're looking through that, you can kind of see some outputs there. Here's a cool video right here that'll also be useful. So our test score deals with the cross-validation piece to it, so that's a pretty good one there. And then our test accuracy is kind of the more understandable one here. So when we tested our data, we were accurate at a little over 93%. So that's some pretty good output for us there. So again, this test score, what that's looking at is the loss function we chose. So way back up here. So it's kind of basing off that how high or low our loss is at that time. So pretty low loss on that test score means we have pretty high accuracy here. Okay, all right. So now that we have a model with over 93% accuracy here, it's pretty simple in the sense that like it's a sequential model. There's go-to errors for it. We're just kind of putting in like one set of data. So if we kind of think about this, we didn't build like a terribly complex model here. Once we got through the cleaning, we're going here and there's not a whole lot going on. We're not doing too much with transformations. We just kind of reshaped our data. And to be 93% accurate at that point is pretty darn good. So what I want to look at next is how we can actually test this model. So to do that, I'm going to type first, and then we'll talk through the code. And then I am going to go ahead and do a quick copy paste here for this. Where are we at? Isn't it like, oh, I spelled response wrong up here. So what this is doing is it's pulling this specific link. So if you've ever worked with URLs in Python, this is kind of how you reference them. And again, this is one of those you need to have the repository kind of things. So if you have some handwritten images locally stored, you can test it this way. And you can kind of download those. You can pick kind of random ones from the data set as well. So you might see some people do it that way. This was just a link I had a long time ago when I did a project similar to this. So I admittedly will give credit to this individual who stores this online. Is I still use that link even today when I teach classes on this. So it's handy, it's this too. And we're gonna go ahead and attempt to classify that. So then what this code does is the response is identifying is using the request model or module package, whatever you want to think of it as, and it's saying get this URL, the stream equals true function just means pull it how it looks. And then the image is saying to open this, and then the im show, like we've seen earlier, we're just showing the image here. And then the next package we're going to use here is what's called Cv2. So it's OpenCV. It's a Python library here dealing with computer vision. So computer vision essentially means taking handwritten or hand-drawn things and making them readable by a computer. So it's a pretty popular package for that. So what we're going to do here is walk through this. So I'm going to say import Cv2. And then I'm going to code this out, and then we'll kind of talk through how to actually read it. How to install Cv2. I don't know if I have it installed on mine on this computer or not. Let me go ahead and try it. Ha, fantastic. We don't have that. So let's go ahead back to the Anaconda command prompt. So to install this from Anaconda, just use that pip again. So pip install Cv2. Huh, they don't like that. Okay, let me see here if I can pull a line on that. My apologies, I ran this on a different device earlier, and I must have already had it installed. Let's see if the conda command works. It's not gonna like that either. Saying that that one is not solved. Let me try it with the other name of OpenCV. So let's see here. Doesn't like that one either. Okay, let me try it this way here and see if this works. God. Ah, fantastic. Great find. So different ways to get that open CV working there. So I just ran the command here that Anjana shared, and then Memojez is there a nice resource as well for looking through that. So getting that open CV open. And then I'm gonna go ahead and just restart my kernel here. And then rerun everything just so it updates with having that installed. Also, if you're looking to quickly run through code like this, if you just hold shift and press enter, that's what I'm doing just to kind of quickly move through my code there. Then we got CV2 working now. So we can go ahead and finish that up. So thank you all for that. Fantastic save as a class there. All right, so we're still gonna call import CV2 there. And then let's see, we're grayscaling. So we want to convert our color. We want to use the resized object. cv2.color.bgr2 gray. Okay. Okay, so what this is doing is it's pulling in this image up here. So this is IMG image of this 2. It's then going ahead and take it and create an array. So it's reading it as an array. So again, here we see our differences inside of this image in terms of looking at the different intensities. And then we're resizing it to be that 28 by 28. So the original one here, we may have some large dimensions. So we're going to get repixelated here to the 28 level. And then converting our color here. So blue gray to gray. So switching it from a blue gray kind of mix into just the gray scale we had earlier. And then this bitwise here is making my image into this. So you can see a lot of intensity in this image. So it's a very dark coloring in there, even after we converted it. So this would be the image that we're looking at here. Then we can kind of see down here. So it converted it to that black white combo. So again, why we did that, if we look way back up here, what we trained our model on, that's how we did it up here as well. So we inverted those colors from what we originally seen way back up here of a white background with a black shading. We inverted them to be black with white, just so it'd be a bit easier for classification. So we took that and then made it into this. And then this is showing the actual input metric we're gonna see there. All right, now, hopefully we're thinking back to what we did earlier, and that is kind of reducing these intensities here. So you see that 255 is still the max there, so just like before. So what we're gonna go ahead and do is say image is equal to image div 255. And then we need to go ahead and do our reshaping. So I'm going to go ahead and say you want to redefine what image is equal to here. So again, go back and check out that reshaping. And again, this is something I said, kind of learning on the fly. If you use the notes we typed above, you should have an idea here of how to get to that reshape. All right, so for that reshaping here, again, if we think the 28 by 28, we want to do that with multiplying. 28 times 28 gives me 784. So our reshape here, we want to do 1 by 784. And then our last output here is just going to be building our predictions. We'll see if we get it right or not. So we're going to say prediction equals NP for NumPy. Depending on if you're looking up any tutorials of this is actually something that changed with the latest update of TensorFlow. So when I was prepping this lesson and looking back at my notes, one of my set of notes to kind of do this was an older one, and it was spitting out an error here. So depending on where you're getting resources from, now you want to make sure you're updated when you're using the newest TensorFlow. So it's 2.4 and some change right now. That's where we have to call it this way. So np.argmax, the max argument. We're going to say model.predict. We're going to use that image that we just reshaped. And then I want to go ahead and get axis is equal to 1. And then I'm going to go ahead and let's say predict. And then I'm going to go ahead and just convert it to a string so it'll print nicely. Now I'm putting this over in the shared file as well. Gave us the wrong answer. So let's talk about some of the inherent challenges here. And that's kind of the goal of this, because we actually built a really good model. We're at over 93% accuracy here. So let's kind of look at why we think it might be wrong. Now, when we're looking at these different inputs here, so the data that we're training on versus learning on. If I go back up here, way up to what I'm looking at. So we can kind of see a lot of these almost looked like they had less intensity in some cases. So we've seen some lighter ones here. So if I'm looking at my 2s, now this isn't the exhaustive measure of the 2s. If we've seen, we actually had, let's see, over almost 6,000 different 2s. However, again, things like intensity play a role in this. So the idea that we want to see how hard someone may be pushing down a pencil and getting that idea. So if we go down here, we've seen that this looks like we should be able to say that's a 2. But with computer vision and when we're doing these predictions, we got close, right? It was a 3 because it had that kind of curvature here. So it was almost reading this curve as being down farther than it was. So how we might be able to improve upon this model. Let's just do a little experimentation here and see if we can get this to get to the right number. Some of you too, depending on how your model trained and what it pulled, it may have, when it did that random selection of the training there, it may have been like a 5 or something else. That's another common one we sometimes get. So let me go ahead back up here to my epochs and let's see if we increase these things a bit, just so we can kind of do a little experimentation. I'm gonna go ahead and change my verbose to 1, and then I'm gonna do epoch set at 50. The reason I changed the verbose there is just so I can kind of get a real-time feedback here on how fast or how long it's gonna go for. All right, moving along pretty quickly there. So it should be done in a few seconds with 50. My 40s. Man, if we would have ran that 1,000, we'd still be waiting. All right, and we're almost good now. Fantastic. All right, so let me go ahead and let's take a look at some of our graphs here. We're seeing those divergence, but let's see if it at least gets our accuracy up to where we'd like it to be. Still getting 3. So with this may be an example of something as we're looking at, even with a good model with pretty darn high accuracy. Because if I look back up here when I reran it with 50, we're still in that 92 range there. So let's go ahead and try if we reduce it now. So we tried. Okay, so someone got a digit of 5. Yes. So Depending on which data it pulled here, it's not always going to give us the same thing, but we're all getting it wrong. It looks like right now I got a 3, Ionis had a 5. So let's try this now with going less epochs. Let's see if we kind of lower it even lower and just stick with that 10. So if we leave it at just 10, let's see the difference here and how that's going to improve or lower our accuracy. So if I keep running on through, we're still getting that incorrect classification. So depending on your model here, again, the way it's pulling data, what data it's using, it can be very challenging to get a model that's actually going to give us the accuracy we need, despite when I'm looking at the accuracy of my model up here, it's still giving me almost that 93% accuracy. So understanding the differences here, it's going to be, again, the inherent challenge with computer vision and classification. This is where the sequential model kind of hits its peak. As we can see here, that even though we're above 90% in our accuracy, that means on any given attempt, there's still about a 1 in 10 chance of us getting it wrong. So a very strong model, you want to look at that 98 plus kind of thing in terms of accuracy, it's reducing that error. Another thing to consider too is the images that you're using to input. Maybe I could say, okay, hey, like this is something I would want to focus on in my twos, is really focusing on this part of it where that curvature comes in that may make it think it's a 3, or the flat lining and then the curvature again, giving that semblance of a 5. So the goal here was for us to understand the idea of a sequential model and how it can be good. Human prediction is more powerful than the model prediction. So that's a great point there. As we look at the idea of computer vision and machine learning, as I started off with that quote, anyone who says they're a master of machine learning and computer vision in our current time period is like a doctor from the 1800s thinking they were a master of medicine, right? There's still so much for us to learn. And this is when people say they're worried about like artificial intelligence. If you ever see the image classification, they call cats dogs and dogs cats. So while it's improving, it's by no means perfect. So what I want to go through at the end of class here is just showing you guys something, I guess, an interesting read and kind of an expansion of computer vision. So if you want to check this out, it's a GitHub site. If you kind of read on down here. So it's a project where they created a fashion version of this. So it shirts and pants, shoes, pretty cool thing here. They also have a really cool 3D visualization here of what the data set looks like, so how it's grouped. So in terms of an assignment or further reading, I'd really like you guys to look through this. So just kind of seeing what the idea of that minutes and how it can be put into bigger context. So here they were looking at 10 different classes when we did our minutes data we had. So when we think about the idea of benchmarking here, this data set, the minutes, is actually pretty common. Anything with computer vision, it uses that as like their benchmark level. So this is kind of a cool thing because it looks a little more 3-dimensional with it. So using this classification. So some pretty cool stuff here, again, for the further reading into this. So we'll kind of see how this one here, working with a different data set, can be a little more intuitive, a little more exciting. So we'll build our models a bit more complex. So if you kind of look through this, this gives you an idea of